Here's the solution to that quiz. We're going to plug a solution of the form n to the alpha into these equations and figure out what alpha has to be for the equation to hold. Well, in the first case, where t of n is 4 times t of n over 2, alpha is log base 2 of 4, or 2. That means the running time is n squared, which means we did all that divide and conquer stuff, and we didn't do any better than the grade school method, which was also n squared. Ah well, bad luck. But then we went back and looked at divide and conquer a little more carefully, and we saw that we could reduce that 4 to a 3. Now alpha is log base 2 of 3, or about 1.6. Now, I know that going from n squared to n to the 1.6 is only going from one polynomial to another. But this still illustrates the point that the algorithm which naively seemed like the best possible one, remember it seemed impossible to avoid doing all n squared combinations of multiplying one digit by the other, in fact is not optimal. There's an algorithm which is significantly faster. You should be asking yourself, well gee, if I can get alpha down to 1.6, how far can we go? How low can we go? If breaking things up into 2 pieces is good, maybe breaking them up into 3 pieces is better. And in fact it is. It turns out that for the problem of multiplication, we can get alpha down as close to 1 as you want. It turns out, quite surprisingly, that you can multiply 2 n-digit numbers in the limit of large N in almost linear time, time which grows like n times log n times log log times log 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 log, but just pretty much n, which is quite surprising if you're used to the grade school method. So sometimes problems are easier than we think, and it's hard to know when you have the best possible algorithm.